Good morning and good evening. I know you guys have good evening there. All right, let's get started. For some of you who are wondering how long you're going to be with me, for some of you who are bored already, we are kind of towards the end of the tunnel. I just got only these topics that I wanted to cover before I let you guys go. Um, One of the important topic I want to cover is normalization, which I'll do today. I want to talk about joins a little bit, then data warehousing, data mining. Um, Data mining is really interesting. I don't think we're going to go into the depths of it, but data mining was one of my specialization when I did my master's. I did data mining as one of the courses I enrolled for. It's very interesting. Again, it applies a lot of algorithms to derive certain things. Okay, so it's very interesting. You will be surprised to know how theory derives something without you even knowing that it does it. A lot of times we apply some concepts and algorithms on it, and you will see it helps you make some decisions, helps you get some data out of a large collection of data. So it's a vast field. If anybody is interested in that, you can pursue your career in that field. Data science, data mining is one such interesting space. um, and I want to touch a little bit about SQL. Okay, so if I look at this, I'm thinking about another 2 to 3 sessions, including today is what we're going to be associated. Okay, so just bear with me for another maximum of 3 more sessions. Okay, probably by end of next week we are done. Okay, all right. With that, let's keep moving. Normalization. What is normalization? So we talked about um, software development life cycle, and then when I talked about SDLC, I talked about we go through analysis, we go through design, build, and test deployment, right? So we talked about yesterday's in previous session we talked about ER diagram. Okay, ER diagram is where you are given a paragraph, and from the paragraph you kind of derived a pictorial representation of the scenario. Yes, how did you draw the pictorial representation? That's where we went through each of the bits and pieces. Sometimes you might have questions in an exam about explain ER diagram. You may be blank to write what should I write. So just write about the parts of ER diagram. ER, entity relationship. So write what is an entity, what is a weak entity, what is a relationship, what is a total participation, what is a weak participation, cardinality and ordinality. These are the main things. Yes. So once you understand the pieces of it and then you put them all together and join them, that's what we looked at this picture. Did I go too far? So this is where we saw this picture last week. Last session. From the requirement that was given, we kind of came up with this diagram. How did we do? Applied the rules. Okay. So you created entities, you created a relationship, and then you kind of put in total, weak participation, whatever it is. I did not, and I showed you the cardinality, ordinality separately as we went through, one-to-one relationship, one-to-many, the minimum number, maximum number, etc., etc. Okay, so that kind of helped us to derive the ER diagram. Then now next phase is to convert the ER diagram into tables, which we did. Okay, I kind of showed you if you have to end up converting that ER diagram into tables, this is where we're going to end up. These are the 4 entities we had in the ER diagram, and these are the 4 tables we're going to be creating. So we will be end up each entity converts to a table. So you have course was an entity, so it becomes a course table. Department was an entity, department becomes a table, student table, and then you start feeding in data into it. Okay, so far so good. All right. I know some of you missed the second half of the session yesterday. If you have questions, feel free to talk to me after today. If you need anything to clarify, I can do that. Keep moving. Listen very carefully with me here. After you create um, this table, we start feeding data into it. Let's say, for example, I take this department table. I feed one row of data, department number, department name is computer science, let's say. And the courses offered are RDBMS, networks, Python programming, whatever. And I have another column called number of professors, let's say 10 professors are in the computer science department, right? Very clear? Now, I'm going to apply or ask for if the features, let's not let's say what are the features of DBMS, or even if you go by cards rule, let's apply cards rule here, okay? Because I said we got to apply cards rule. We got 13 cards rule we need to apply on these tables to make sure if they qualify for an RDBMS or relational tables, right? So let's apply one of the cards rule. The first cards rule, I believe, says every column must store an atomic value. Okay, you guys with me? Atomic. The term atomic means each column should store only one data, not a set of data. So if you look at the courses offered column here, it's storing in a cell a non-atomic value, meaning it's storing three data here. RDBMS is a data, networks is a data, Python programming is a data. So this does not satisfy CORD's rule. So CORD says for it to be called an RDBMS, relational table, it has to have, each cell must have atomic values. So what it means atomic is only RDBMS must be there in a cell, only networks must be in another cell, Python must be in another cell. How can I do that? I have to break it and bring it to the next column or next cell. Yes? With me? Oops. So here what I have to do is I have to store each course in a separate cell, and then I have to duplicate this data here. Oops. Okay, so just for the sake of storing the different courses, I'm duplicating the records, but I'm changing the courses offered. So if you look at the whole record, now it applies CORD's rule. So the CORD's rule says each cell must have atomic value. Yes. Each of them has only one data in each cell. Yes. But now let's apply. I'm going to ask the features of DBMS. I know some of you sent assignments yesterday. I think one of the question I had was, what are the features of DBMS? And the very first features that comes in is what? Controlled data redundancy. Yes. Basically, the intent is to avoid data redundancy. I explained what is data redundancy earlier. For example, here, the department number name is repeated 3 times here. Because I have to satisfy CORD's rule, it is not satisfying the features of DBMS 100%. It is satisfying. If you look at the whole record as one, it is unique. Yes, no two records are similar. No two records are similar, but part of the record, a group of data is repeated here, right? Department number and his name, department number and name, which is basically a redundancy. Again, the number of professors. Assume there are 20 columns and just the courses column has to be atomic. So just for the sake of course column, I'm repeating 19 other data, 19 other columns, which is really not very good for an RDBMS. Make sense with me so far? So as a group of data is being repeated multiple times, which is against the feature of RDBMS. So now we have to work on it. Okay, we'll park that for now. That's what normalization is going to do. Next. So this is an example, same thing here. I cut student information. The whole first 4 records are student information. I'm storing student number, student name, address, date of birth, course ID, course name, and the marks. I have to have separate records for each student to store their course ID and course name and marks. But what is repeating here, the student record details are repeated the number of times I'm storing the course record. If I'm storing 10 courses, I have to repeat the student information 10 times. Make sense? So this is again against the feature of RDBMS. Okay. Same here. If you look at professor table, so usually it says professor ID, professor name. Let's say I use my name, and specialization. I put all the subjects that the professor specialized in expert system, DSS, RDBMS, AI, neural networks, FTS, whatever. Again, this is not atomic. Okay, so we need to break it into multiple rows. So let's go back into normalization. Let's talk about it, what normalization means. So what we have done is, from the requirement, we ended up with the ER diagram. From the ER diagram, we moved into tables. Now we realize that the tables are not fully normalized or does not satisfy all the features of RDBMS or the chords rules. So we're gonna do normalization on the tables. Okay. So what is normalization? Normalization is organizing data in a database or a table. Okay. You're organizing the data in a database or a table. You're basically normalizing the data. You can use the term normalizing the table, but that's not going to fetch you marks in your exams and doesn't give you an answer, right? Normalizing, what do you mean by normalizing? It's more like optimizing, if I can use the term optimizing, because I'll tell you why at the end of the normalization. You know, you cannot really have a 100%, um, cannot have a table that's 100% satisfying the features of RDBMS, 100% satisfying chords rules. That's never possible. If that is what has to happen, every table will have only 2 columns. We'll see why. Okay. Now, you have to organize the data to be efficient in a database or a table and restructuring the tables to reduce redundancy. So that's the important agenda of normalization. See, I showed you the redundancy, right? For example, I showed you the professor table. The professor ID, professor name has to be repeated multiple times for each course that he is teaching. Okay. So in order to avoid that, we're going to reduce the redundancy. In order to reduce the redundancy, I'm going to restructure the table. When I mean restructure, what I'll be doing is I'll be ending up breaking a table into multiple tables, and each table will have fewer columns. If there are 10 columns in a table, I might end up breaking them into 2 or 3 tables, and each table will have 3 or 4 columns. Make sense? So far with me? That's normalization. So within normalization, there are multiple normal forms. Usually there are 5 different normal forms: first, second, third, fourth, and fifth normal form, and then we have Boy's card normal form. Your your textbook is more talking about first, second, third normal form primarily. It's just defining what is Boy's card normal form, but no table satisfies all the rules of Boy's card. Remember that. When you have questions and exams about Boy's card normal form, you can write this statement. You can write about Boy's card and say, practically no table satisfies all 13 chords rules. Okay, remember that. I'll tell you why later. Okay, let's keep going. First normal form, to be put very simply, if you look at your textbook, it kind of talks a lot of items. I don't want you to go through all of it and get confused. I'm gonna just give it in 2-line definition. Um, okay, so don't worry about all this. Just take 2 lines of what is first normal form. So we're gonna talk about first normal form. So if you are not following what I am doing, I'm gonna request you note down the tables that I'm using. It'll be more easier. I looked at the examples used in the table. They do not make it easy for you to understand. I mean, they have content in it, but I think the examples that I might use may be easier for you. So if you could grab a piece of pen and a paper, just note down the examples that I'm using, it'll be great. I'll try to share this document, but not immediately. Later, when I kind of scrub it a little bit. Um, but I'm gonna request or ask that you take a piece of paper and a pen, note down these pointers as well. Okay, these bullet points and the tables. Okay, moving on. What is a first normal form? A table, usually a table is said to be normal form. A table is said to be in first normal form if and only if 2 items are satisfied. What are the 2 conditions? Each column has atomic values. I told you what is atomic values. Each cell must have only one data. It should not have a group of data. Number 2, there are no repeating group of data. Repeating group, for example, I showed you an example, professor number or professor ID, professor name is being repeated in a table for every subject. Or for example, student ID, student name, address, date of birth being repeated multiple times. These 2 should not be there, meaning there should not be a group of data in one cell, and there should not be repeating redundancy of data. If I take those 2 conditions or anomalies, I'm going to use the term anomaly. Usually this term is used in DBMS. If I take these 2 anomaly out of the table, then the table is said to be in first normal form. Make sense? So let's assume this is the table example that I used. As soon as I converted my ER diagram into the table, I ended up like this. You guys have to tell me if you need to slow down, stop me. I know some of you are taking notes. So I assume you noted down those 2 points. Okay, no atomic values, no repeating group of, no group of data. It has to be atomic values and no repeating group of data. Now let's assume after I convert my ER diagram, one of my entity turned into a table like this, where I have course number and course name within one cell and their respective marks in the other cell. So no atomic, that these two columns do not have atomic values. So I'm going to convert this table. See very carefully. I need to store atomic values. What I'm going to do is, since student number, student name are repeating, I can keep them in one table. I'll have student ID and student name in one table, and I'll break the course is what is getting a group of data in each cell. It does not have atomic values. I'm going to create a course table to say course ID and course name in a separate table. I'm storing course ID and course name in a separate table. Okay. And again, I'll store the marks and the grade in a separate table. Okay. The marks, student ID, course ID, the course that he is enrolled in, the respective marks and the grade that he has got. So if you take the whole record is unique, the whole record is unique, no group of values, course ID, course name are separated, marks is unique, okay, no repeating groups here. I mean, these are all atomic values. Make sense? So now what has happened is that these 3 tables are in first normal form, but one table is broken into 3 tables. Okay. So this is what will happen as you go down the path of normalizing a table. As you start normalizing a table, you will increase with a multiple number of tables, but you will see each table will satisfy uh, close to Codd's rules and the features of DBMS. I'm going to slow down to ask questions. If you don't understand first normal form, there's no point in going to second and third. At least give me a confirmation that you guys are with me. If you want me to repeat, I can. No need to rush. Okay, I got a couple confirmation. Good. Okay, so that's about first normal form. Very good. Okay. All right. So let's keep moving. Second normal form. Okay. So first normal form, again, I'm repeating. I quickly said each column should have atomic values. You cannot have a group of data in any column and no repeating group of data. Okay. So we avoided the repeating group. For example, if you looked at the table that we had before, had repeating group of data. For example, here, the student ID, student name, date of birth, are repeating. So we don't have that because we've broken down the table into student table and course table. So we don't repeat student number, student name, address, date of birth, etc. We don't repeat that. Okay, so repeating group of data is reduced. I'm not saying avoided, I'm saying reduced. You remember the term, because we cannot completely avoid it. Okay, we reduced it. Okay, now moving on to second normal form. In second normal form, a table is said to be in second normal form if and only if these 2 conditions are satisfied. The table must be already in first normal form. So you cannot directly go to a second normal form unless the table is already in first normal form. So you have to make sure you normalize the table and it is in first normal form before you go to the second normal form. And the very important rule for second normal form is the table should not have partial dependency. Remember the term, okay? I'm going to use this new word. You will not find it in the textbook. I'm going to use this term. The table should not have partial dependency. What is mean by a partial dependency? A non-key attribute depending on a part of the primary key. Follow with me. If you're sleeping, wake up yourself. I usually say, if it is a classroom setup, I usually say each neighbor wake up the person sitting next to you, but I cannot ask this here, okay? So I don't know what to do here, but you have to follow me here. Partial dependency, okay? A non-key attribute depending on a part of the primary key attribute. That's where the term partial comes from. What do you mean by part here? Okay, we guys, let's quickly remember what's a composite key. A composite key or a composite primary key means more than one column together identifies a row uniquely. So in this table, this is the table that we had, one of the tables that we had in our first normal form. When we broke down the table, we ended up on one of these tables, right? In first normal form. Oops. So this is the table we had in first normal form. I'm going to continue using the table. So here, my composite primary key is student ID and course ID, because if you remember, we talked about this. Just with the student ID, I cannot get a record uniquely because I have multiple records for each student. So I cannot use student ID. Same with course ID. Just with the course ID, I cannot identify a record because there may be multiple people who have enrolled in the math subject. Okay. So what I'm going to do, I'm going to use student ID and course ID together as composite primary key. A composite primary key is nothing but more than one attribute or a field working or acting as a primary key for the table. Yes? Okay, now the point here is a non-key attribute. What is a non-key? The attributes other than the primary key or key attributes are called a non-key. So in this table, other than student ID and course ID, rest of them are called non-key attributes. Course name is a non-key, marks is a non-key, and grade is a non-key attribute. Okay, a non-key depending on a part of the primary key. What does that mean? Now tell me, if I need the course name, I need to know the course name. Can you give me the course name if I give you the course ID alone? I'm giving the course ID. I'm asking, let's say, for example, I'm asking Alok. Alok, can you tell me what is the course name for the course ID C003? If that is my question, what will be your answer? Alok, you with me? So what is the course name for the course ID C003? So if I go into the table, okay, I got the answer. Thank you. So, okay. So chemistry, yes, because just with the course ID, I'm able to identify this course name. So follow along with me carefully. So the course name is a non-key attribute. To identify a non-key attribute, I'm using course ID, which is a part of the primary key. Course ID is not the primary key. It is a part of the composite primary key. So this is what I mean. The course name is dependent on the course ID. What is the meaning of dependent? To identify. If I need to identify the course name chemistry, all I needed was a course ID only. Irrespective of whoever enrolls, whether it is Alok, Achyuta, Priya, whoever it is, whoever is enrolled, I don't mind as long as I know the course ID C003 is chemistry. Yes. So a non-key attribute depending on a part of the primary key. This is what it is, partial dependency. So this should be removed so that the table is in second normal form. So this table is not in second normal form. So to bring it to second normal form, what do? We gotta again break this. um, all right, looks like there is a little bit disturbance. Is that for everybody? One of you have pinged me that you cannot hear me properly. I don't know, it may be a network issue, but if multiple people have, please quickly ping me on the chat if you cannot hear me well, okay? All right, so assuming everything is fine, I'll keep going. So what should I do now is I have to remove that partial dependency. How can I remove? So these two people who are dependent on each other can go become a new table, okay? And then I'll make this as a primary key. So after second normal form, what happens is I'm breaking the table, I'm bringing course ID and course name into a separate table, and rest of the columns will reside in the other table. So course ID, course name, and all the course related data. Okay, the credits for the course, maybe if you're storing who is teaching that course, what is the classroom that the course is taught, what's the building number, whatever it is. Okay, the course details come here. And rest of the data. What is the rest of the data? Student ID, marks, and grade can stay in the other table. But remember, I cannot take the course ID out of the other table because it's a composite primary key. The course ID has to also stay there because without the course ID, I don't know the marks and the grade for the student. So all the course related data will come to this table. Make sense? But still course ID will stay here. Now, what is the connection between these two tables? Now, if I'm asking you, what is the marks of student 2 in chemistry, first you need to know what is chemistry. So you're going to find what is chemistry here. It is C003. With that, you come to this table, you find the course ID here, the student ID, and then you get the marks. So now I'm going to ask a question again. What is the role that the course ID is playing in this table? The first table. What is the role course ID is playing here? The course ID is playing the role of a primary key, because just with the course ID, I can identify the course name, or if there are other columns in this table, I can identify them using course ID. So course ID alone plays the role of primary key in this table. And in this table, what's the role of course ID? Remember, I said a primary key, when it goes to another table, it becomes a foreign key or a foreigner. So your course ID is a foreign key in this table. Student ID and course ID together form the primary key. I don't know if it's too much to understand for people who are new to these terms, but please understand three things I'm talking about. Course ID is a primary key in this table. Course ID is a foreign key in the second table or the child table. Course ID and student ID together form composite primary key. So far so good. Now if you apply the rule of the second normal form, the second normal form says the table should be already in first normal form. Yes, they are in first normal form because each of them have atomic values. So that condition is satisfied. The second condition says no partial dependency. There is no partial dependency here because all of my non-key depend fully on my primary key. They do not depend part of the primary key. Course name depends on course ID, which is my primary key. Marks, for me to know the marks, if I'm asking you, tell me the marks, your question will be for which student and for what course. Yes? You cannot just give me the marks if I tell you the student ID. You will ask me two things. What is the student ID? What is the course ID? So you're asking me two things, and both of them together form the composite primary key. So that then all the non-key attributes are completely dependent on, same way with the grade. It is completely dependent on the primary key. So there is no partial dependency. And non-key is not depending on part of the primary key. So the tables are set in second normal form. Keep moving, third normal form. Third normal form. A table is set in third normal form if and only if the table is already in second normal form. Okay, agreed. It's like a step-by-step process. So you put it in second normal form, and also there is no transitive dependency. I'm introducing the term transitive. Okay, transitive meaning a non-key depending on a non-key attribute. You know what is a non-key attribute? Which is not part of the primary key. So if there are two non-key attributes and each of them depend on each other, then it is called a transitive dependency. So here if I ask you what's a grade, your only question will be what's a mark? Because your grade is dependent on the marks. It is not dependent on who has got that mark. Yes, and in what subject. If I ask you, for example, we got Vamsi here today. So if we say Vamsi has got 100 marks in math, I don't need to know whether it is Vamsi or Sai, whoever it is. You tell me the marks, I'll tell you the grade. Yes? It is not going to act like, okay, if your Vamsi has got 100, it is A plus. If Veena has got 100, it is B plus. No, it's not. Irrespective of whoever has got 100, it is A plus, right? So it is not going to ask me anything else other than the marks. So for me to give you the grade, I need only the marks. So here, unfortunately, both of them are non-key attributes. Grade is depending on the marks. To identify the grade, I am depending on the marks. So both of them are non-key. A non-key attribute grade depending on another non-key attribute marks is called a transitive dependency. I cannot have transitive dependency here if I have to go to third normal form. So for me to break it, I'm gonna break this table into two again. I will store the student ID, course ID, and the respective marks in one table. And I create another table, marks and grade, where I will say if the marks has been 100 to 90, it is A plus, from 89 to 80 is A, and so on and so forth. So now what I'm doing here is, one thing, redundancy is reduced. So if I had about a million records stored, I had a million grades stored. Do you agree with me? Assume in a huge college database, if I have a million student records, I'm storing this data for the million students. I'm storing the grade for a million students. I don't need to store their grade a million times because, like I said, irrespective of the marks, their grade remains the same. Okay. Um, Guys, if we get disconnected in a minute or two, let's join back in the same link. I'll be back with you shortly. Um, all right. Okay, going on. So what I'm doing here is, irrespective of a million records, I will only store these 5 rows for the grades table. Yes, because irrespective of the million students, if you get this mark, this is your grade. So I'm reducing redundancy as well here. You're with me? I'm removing transitive dependency. I'm reducing the amount of data that I stored in the grade table. Plus, I'm also reducing the storage because I stored a million cells here, million cells of data. Whereas by moving it as new table, I'm storing only like 10 cells, 5 cells of, 5 records of table with 2 cells of data. 5 by 2 is 10, right? What does it save? It saves me space. It saves me the amount of data. It reduces redundancy. Make sense? So now these two tables, none of them depend on non-key attribute. I mean, you don't have anything else at all. There's only one non-key. There's nobody else to depend on this non-key. So no transitive dependency. Same way here, there's no other non-key. It's only one non-key attribute. So no transitive dependency. All right, makes sense? So that's what third normal form is all about. Third normal form quickly says the table should be in second normal form and there should not be any transitive dependency. Transitive dependency meaning no dependency, right? A non-key depending on a non-key. Let me quickly go through that. I don't know if actually this question was related to that. So grade was dependent on marks. Why? Because if I know the marks, I can decide the grade. So the decision of grade is based on the marks. That's what it means depending on. So the grade is depending on the marks. So that's the reason why we call it a transitive dependency. To remove the transitive dependency, we are breaking the table into a separate table. The grade and marks are separated. Okay, so it goes in a new table. So what has happened here, the one table is slowly broken into multiple tables. We have a course table, we have a student table, we have a marks table, we have a grade table. There are 4 tables that we ended up. So that's what I say, as you keep going, doing the normalization, the number of tables that you end up increases, right? We started off with one single table, which had student number, course ID, course name, marks, everything. Now we are ending up with 4 tables. One table just for student ID, student name, student details. One table for course details, course ID, course name, the credits for the course, etc., etc. And then we have one for storing the marks, student ID, course, and marks. And we have another table for grade, marks, and the grade. Remember here, I have not even talked about the professor who is teaching the course. If I had that information, there'll be another table, all right? So as you go to the advanced form of normalization, a single table will be broken into multiple tables, as well as the number of columns in each table will reduce. So that's where I say Bcnf, Boy's Chord normal form, it's what I'm going to talk next, is an enhanced version of third normal form. It's an elevated form of third normal form. So when you do that, I usually say your table will have only 2 columns. 2 columns, the first column will be the primary key, the second column will be the foreign key connecting to another table. Student ID, course ID. Course ID will connect to the next table. The course table will have course ID, maybe the professor ID. Professor ID connects to the professor table. So, just it's not exactly true, but most of the times you will end up with only 2 or 3 columns in the table. So this is practically not possible Understand? The practical is always different from the theory. So Boyce Scott talks about 100% perfection. Nobody's 100% perfect. So no table is in Boyce Scott normal form 100% in practical life. Okay, they follow Boyce Scott normal form, Boyce Scott rules to a certain extent, maybe like a 50%. Okay, but not 100%. All right, I'm going to talk quickly about what is Boyce Scott normal form and keep going. All right, Boyce Scott normal form is nothing but an higher form of third normal form, or is an enhanced, elevated, or advanced form of third normal form. Okay, Bcnf is a higher form of third normal form. Okay, in Bcnf, it asks that every determinant must be a candidate key. Determinant meaning somebody who determines a value, meaning a mark determines the grade. Yes, so mark is a determinant. So mark must become a candidate key. That's what we did in third normal form. We made marks as a primary key. Okay, that's what I said. And it is an elevated form of third normal form. Every determinant must be a candidate key. Here in our table, okay, let's go. So in our table here, the previous table that we had, marks was determining the grade. So mark was determining the grade. So mark was a determinant, okay, and grade was being determined. So if it is a determinant, it should become a candidate key. That's what we did. We broke a new table. We made marks as a candidate key. Okay, so it also says no non-key attribute can depend on a non-key attribute or part of a candidate key. Again, same rule as third normal form. Transitive dependency. There should not be a transitive dependency. Okay, so if there is a question on Bcnf, just highlight your key items. Bcnf is an highest form of third normal form. It expects that it follows all the rules of Boyce Scott rules, 13 rules, but in practical purpose, for all practical purposes, it does not do that. If it does, a table will have very minimal number of columns and it will be broken into multiple tables, and you can write these two rules that we talked about um, in third normal form. Okay, every determinant that determines a column must become a candidate key, and a non-key cannot depend on a non-key, meaning there cannot be transitive dependence. Make sense? I don't want to deep dive too much there because it's not a point of interest at this point for you. These are like, we do in our, in a specialization on DBMS. That's where we deep dive and do a lot of analysis. All right. I'm going to give a quick pause. If anybody has questions for anything, I'm happy to answer. But otherwise, I'm going to continue to talk about, I think I want to talk about joins today a little bit. We got few minutes until you guys are bored. I'm going to talk a little bit about joins, and with that, I might be able to stop and we will do the rest tomorrow. Okay. Again, any questions, feel free to stop me. All right. Joins. So joins are nothing but, you're connecting two tables. So we are slowly getting into implementation part. Okay. I mean, still, I'm not talking about the SQL, but I'm going to talk about how do we use, so far we talked about these phases of SDLC, right? We talked about designing ER diagram, and then we talked about converting ER diagram to tables, normalizing them. So kind of you have created tables, you have normalized, you now got a pretty solid tables to use, and you can start putting data into it. Once you start putting data into it, the intent of data is put and to store and retrieve. Now we're going to talk about using multiple tables. How do we combine data from multiple tables? A lot of times this is what happens in practical life. Okay, you will have data in multiple tables. Like for example, we saw student table. We had student ID, student name, then we had course table, we had professor table, and then we had marks table, we had grade table. If there is a question about, can you give me the details about a student who are all enrolled in the course computer science who has got, let's say, a B grade, okay, for some analysis purpose, or students who's enrolled in computer science who are taught by Professor MarieDass, let's say. Somebody wants to know who are taught by MarieDass. So you're talking about three different tables: a course table, a student table, a professor table, right? So this is what is joins, meaning you're using multiple tables to fetch the data. The data is fetched from multiple tables, and then it is presented to you. You don't create a new table, it is presented to you. Fetching data from multiple tables and presented to you in a user interface. it could be an UI, it could be just an SQL a view, whatever it could be. Okay. um, all right, so let's look at this. I just put some random example here. We got table 1 and table 2. This is from the content is from a textbook. Let's assume the table 1 has a column called alpha 1 and number 1. There is a second table that the header is called alpha 2 and number 2. The column names are alpha 2 and number 2. Now, when I generally do a join, okay, let me go back to your textbook. Yeah, I'm sharing a textbook. Let me know if you cannot see it. I'll take the example to make it easy from your textbook. Sorry for that. Too fast. All right, so here is where it talks about joins. This is about, okay, let's use this example. If you can closely follow for people who are new to the CS, computer science, you might need to slightly understand. There are two tables here, okay? I'm talking about table 1, R, and another table S. Table R has called column A and column B. Table S is called column S, column A, S, column B. Now my question, my requirement says, my client says, can you give me some data based on this condition? If the data in column A of table R equals or matches with S column A of table column S, of table S, meaning if the data in the first column here matches with the first column here in this table, give me the data, give me all the columns. So what you're going to do, you're going to check the first row, first column. A matches with the second table A. So the condition of matching is only these two columns, column A. Okay. So you are checking the condition as the first cell, the data in the first cell matches with the data in the first cell or first row of the second table. Yes, A and A matches. So because A and A matches, they're asking all the data. So I'll give the whole row. A1 is the first row, A1 is the first row. I join like this. So the data that I'm looking at on the screen will be like this. A1, A1. Make sense? Now I'm going to match this A with the rest of the column. The first row with the second, third, and fourth row. So A does not match with any of the other rows. C, D, E does not match. Leave it. Let's pick up the second row here now. Pick up B here, and then I'm going to check with all these here. Do I have B here? A, C, D, E? No, I don't find B. So it's not matching. I leave it. Now I take the next row, D, and then I'm trying to match. Does D match with any of these here? Yes, I find a matching here. This D matches with this D here. So I pick up that data. So the row from this table plus the row from this table, D3 and D3 here. Same way. You're with me? This is called a join. I am joining two tables. This is generally done when the data resides in two different tables and they are connected using a foreign key. So column A could be a foreign key of primary key of the table, could be a foreign key, but not necessarily. I can join based on non-key values as well. Remember that it's not always that you should match only on key values. It could be on non-key values. If a condition is used saying, try to match data from this column and this column, you start matching them. You write a condition saying table name dot column name equals the second table name dot the column name on which you are matching. Make sense? You guys are with me? So this is called a join. I'm joining two tables based on a condition. Okay, so this is basically called a join or a simple join or a natural join or called an inner join. Inner join meaning I'm getting data inside of the condition. Only if the condition matches, I'm getting the data. I want you to understand because I'm going to slowly talk about outer join. There's a term called outer join. So I want you to understand inner join before I go to outer join. So inner join, simple join, natural join, they're all same. Okay, you're trying to match data between two tables based on a column condition. You can ask me, should it be only on two tables? No, it could be on multiple tables. I can join three tables based on multiple conditions. One condition saying from the table R, between table R and S, if the column A and column column A matches, and as well as use the logical operator. And let's assume you have another table called a T. So if the S column A and T column A matches, then get me the data, which means there are two conditions I'm applying. These two tables plus the other two tables. So I can write multiple conditions using an AND condition, or I can use an OR condition. I can use an union. I can use an intersection. I can use except, minus, whatnot. Anything that you do in relational algebra can be done here. Okay, makes sense? Joins is clear. I know it may be a little difficult to understand, but just go through this example one more time when you get some time, and you come back to me when you don't understand that. We can talk more tomorrow. So simple inner join will get data only if the condition matches. Now slowly moving on, I want to talk about outer join. What is the meaning of outer join? There are three types of outer joins: left outer, right outer, full outer. Okay, this is where I want to shift to my example. Let's shift to my example here. Let's assume I have this table 1, table 2. They have these two columns and these two columns. They have this data filled in here. Now, I want data from table 1, okay, if they match on the first column. If alpha 1, data in alpha 1 matches with data in alpha 2 of table 2, give me the data, as well as give me the data from table 1 even if they don't match. Get what I'm saying? This is more like an example. I'm saying I want all the details of an employee table plus the details from the spouse table if they are married and have a spouse. So if I take an employee table, assume I have 1,000 records. Of the 1,000 records, if 500 employees are married, I have a spouse. So for that 500 employees, I want to compare between the employee table and the spouse table. If the employee table has a spouse, if the employee in the employee table has a spouse, so I'm going to match based on the employee number. If employee 1 in the employee table is present in the spouse table, E1 and E1 match and get the employee data as well as the spouse data. If they don't, still give me the employee data. You get me? If they don't have spouse, that's okay, but still give me the employee. So what you're doing is you're basically getting all the data from employee data along with the spouse information, which is the second table, if they have that information present in the table, if they're matching data. Even if they don't match, give me the employee data. Don't give me the spouse data if they don't match. Make sense? So if I call table 1 as a left-hand side table during my query, while I'm writing my query, if I use table 1 as my left-hand side table, I call it left outer join. What I explain now is a left outer join, meaning outside of the matching condition, give me the data. Even if the condition does not match, give me the data. It's called outer join. Make sense? Now, if I reverse the condition and say, get me all the data from table 2, which is my right-hand side table, if they match on alpha 1 on the left-hand side table, plus all the data from table 2, even if they don't match, okay? That is called right outer join. Now, the third example talks about full outer join. What is a full outer join? Get me data from both the tables if they have a matching condition, plus get me data from all the tables, even if they don't match. So first you will see all the matching records. Then it will give you data, all the rest of the data from left-hand side table. And for the right hand side table, it will fill in all null. And after that, it'll give me all the data from right hand side table. For non-matching records, it puts all null for the left hand side table. This is called a full outer join, meaning I have data from both the tables if they match, as well as even if they don't match, I have all the records. Makes sense? I want to slow down, stop here. I will go into the examples. I just want to touch upon when we start back on next session. I will talk a little bit more, but I just want to throw the concept at you so you will kind of start assimilating over the weekend. And when you come back on Monday, you can ask me questions, or I can start on a little bit with showing you the examples. Okay, so simple. To talk about joins, we talked about natural join, simple join, where it gives you only data from the tables. For now, we limit only to two tables, but it can be on multiple tables. If I get only the matching records from two tables, from two or more tables, it is called natural join or inner join. If I get the matching records plus the non-matching records from the left-hand side table, I call it a left outer join. If I get the matching records plus the non-matching records from the right-hand side table, it's right outer join. Matching records plus non-matching records from both the tables, it's full outer join. That's where we want to stop today. All right, let's open up for questions. Questions, concerns, open floor, open for any discussion. Feel free to open up and ask questions. How is it going otherwise? Are you guys bored of seeing me for, I don't know, been a long time, close to more than 7-8 sessions so far. So, and I want to understand if it's too boring, I can rush a little bit, finish off. If you guys think we are at right pace, we can go for as per my plan, I should be done. I want to talk about data warehousing and in the next session tomorrow, and I will touch upon SQL a little bit and one more session on SQL. So probably two more days, you'll be with me and then we'll be done. Okay. All right, I'm going to stop the recording. So thanks everybody for your time today. But I want to be here for another 5 or 10 minutes to take up any questions, any feedback, any comments, anything that you want to provide. All right. Thank you guys for today.